You don't want to put it there, all those wires to get through.
Yeah, I'll put it over here.
It looks a little better than a regular plastic bottle.
Hi, everyone. We're going to start the second plenary session. So, yes, I'd like to also welcome everybody from the PTTI side. It's my great pleasure to welcome Dr. Elizabeth Donley to give our plenary speech. I first worked with Liz when I first came to JPL over 20 years ago when we were working, JPL and NIST were collaborating on a flight mission that never got to launch because the shuttle got killed. That was a cesium fountain, that was a fountain-like thing that was going into space. But since then, she has evolved. You will see from this bio all the great things she's done. And I'm just so pleased that she agreed to come today because one of the things she'll be talking about in her refresh for frequency control standards talk is these two IEEE documents that she has spearheaded revising. And I'm just so glad that everyone's here to hear about them because I feel like these need to become the Bible of this field. Everything noise related, everything, I feel like it's decades of people's work, and there was a whole committee of people on both of these standards, and I got to be balloter for both, and I put in so much time just reviewing them. I can't even imagine, she'll tell us, the years of time that went into these. And I feel like it's just a lifetime of people's expertise that got documented for us to know and see and hear. So she will bring them to life as well as tell us other things. So let me give you the proper introduction. Dr. Elizabeth Donley is chief of the NIST Time and Frequency Division, and has served as working group chair for the revision of these two IEEE standards I was just telling you about, 1139 and 1193. And I don't know if there's a reason that their numbers are so related, but it makes it easy to remember that they actually are related, so it's interesting. She's an experimental physicist by training with research experience in Bose-Einstein condensation, the maintenance and development of NIST's atomic fountain clocks, NMR gyroscopes, and the development of compact cold atom clocks and inertial sensors. So she's done a wide variety of things across this field. She has authored or co-authored close to 100 papers in technical journals. She has been serving as chief of the Time and Frequency Division since November of 2018. Her service to the time and frequency community includes organizing symposia and training at national and international conferences, serving as VP for frequency control for the IEEE UFFC Society, and advising graduate students from the University of Colorado. She has also served as the working group chair for the revision of two IEEE standards on the topic of frequency control. She received her BS in physics from the University of Nevada, MSc in physics from the University of Colorado, and a PhD in natural sciences from the Swiss Federal Institute of Technology, Zurich. Please welcome Dr. Donley.
Good morning, and thanks very much to Daphne for the very kind introduction. I'd like to sincerely thank her and the program committee for the invitation to give this talk. It's a real honor for me, and it's also humbling to be speaking here about this in front of all of you. And I'm happy to have the chance to talk about frequency control standards development work that was sponsored by the IEEE UFFC Society, and then also processed by the IEEE Standards Association. And I'd also just like to acknowledge my employer, NIST, for supporting me while I worked on these projects. But before I move on, and I think there's a laser pointer here, I'd just like to admit that preparing this talk has been a challenge, and that's because the topic of standard definitions for frequency control isn't the most interesting subject for a broad audience, unfortunately. Fortunately, this isn't too broad of an audience, so hopefully it goes okay. I'll do my best. I've tried to include something for everyone. But while I still have your attention, I just want to explain, or the reason why I've been invited to give this talk, as Daphne mentioned, it was these two IEEE standards that I chaired the working groups for. So let's see here. This is a little hard to read, but so the first standard that we developed is called IEEE Standard Definitions of Physical Quantities for Fundamental Frequency and Time Metrology, Random Instabilities. And there was a large group of experts on the working group that revised the standard, and many of those folks are in this room. Also, a large group of technical experts served as ballotters, including our program chair, Daphne. I want to acknowledge also the IEEE liaison, Vanessa Lilite, who coordinated with us. And I just want to emphasize that these folks, they didn't just give their time, they also contributed significant insight and expertise to the process. So thanks very much to everyone. We developed a second standard, or revised it. This one is called Guide for Measurement of Environmental Sensitivities of Frequency Standards. It had a different working group, some of the same people, some different people, different group of ballotters as well. This revision was just approved by the IEEE Standards Board last month, and it should be published soon. So to orient us, I'll give a brief outline of the rest of the talk. So I'll start with a discussion of standards development and give some background. And then I'll talk about the they named IEEE standard definitions of physical quantities for fundamental frequency and time metrology. And this, while it wasn't reflected in the title, this was actually a document that focused on random instabilities. And so right around the time that that was published, they formed another working group to focus on environmental sensitivities, and they came up with this document, IEEE Guide for Measurement of Environmental Sensitivities of Standard Frequency Generators. And that was published in 1994. And then on the 10-year cycle, it was, and those arrows look a little off maybe, it was renewed in 2003. So it hasn't been renewed again until now. So it was a little bit, or a lot delinquent with respect to this 10-year cycle that they expect these to be renewed. Now, in comparison, the standard on random instabilities has managed to stay current. So it was renewed in 1999 and then again in 2008, and the name has stayed the same. But it was changed in 1999 to reflect the emphasis on random instabilities. Okay, so now I'll spend the next several slides talking about IEEE Standard 1139. I'll emphasize some things that are new in 2022. And I'll start with just some general terms. So let's just look at some general concepts. So if you have an output of a frequency standard, usually it's a voltage, and you can break down the noise seen on that output voltage in terms of pure amplitude modulation or amplitude noise, where the zero crossings stay the same but the amplitude fluctuates, and pure phase fluctuations where the amplitude stays the same and the zero crossings fluctuate. So these are complementary here. You can express it as just a voltage as a function of time, where you have some noise term in the amplitude and a noise term in the phase noise. And you can also express the phase in time units, which is convenient. So you can just have it as a sinusoid of function t plus x of t. And I'm not going to say anything more about amplitude noise. So that's not the emphasis of the standards. So let's just first talk about the frequency domain. For characterizing phase noise in the frequency domain, the most common instability measure is what we call script L of F, which is just 1/2 of the power spectral density of phase fluctuations. And S phi of F, this power spectral density, it's defined as the mean squared phase fluctuation in the frequency band, delta Fk divided by that frequency band. Okay? So you can get a very good estimate of this power spectral density of the phase fluctuations with a spectrum analyzer that calculates the Fourier transform. And this is a very pure way of characterizing the noise. There's basically just one power spectral density of phase fluctuations. This quantity, script L of F, it's historically used. It has the units of dBc per hertz, and that is intended to mean dB below the carrier per hertz, but it's not a perfect definition of a unit because, of course, if you have strong phase modulation, it breaks down, but it's still used, but it doesn't always mean dB below the carrier. And the phase instability is most often characterized by a plot or table of script L of F or the power spectral density itself versus F. And this is usually presented on a log-log plot like this. And it turns out it's very useful to present it this way because you can by the slope of the different segments in the curve and the positions on the curve with respect to the noise level, they'll help you figure out the types of noise that are present and their amplitudes. So it's a very useful way when you characterize the power spectral density of the noise with power law. Okay. We'll come back to this in a few slides, but first let's talk briefly about the time domain. And so we define an instantaneous fractional frequency deviation, y of t, which is equal to the instantaneous frequency minus the nominal frequency divided by the nominal frequency. So it's normalized. And the standard frequency instability measure that we use is the two-sample Allen variance, shown here, which is just the 1/2 of the mean squared frequency differences between adjacent frequency averages. Okay, and the frequency average is just an integral over the parameter y of t, the fractional frequency over the period tau. And if most of us, I think, are familiar. If you're not familiar already with the Allen deviation, you know what, or Allen variance, you know what classical variance is. And the classical variance looks a lot like this, except you have a mean that you compare each measurement to, and that determines the scatter. Here, for frequency standards, the mean isn't always well defined because for some types of noise, that value changes. And so instead, we use the scatter and adjacent averages to characterize the noise, and that's well defined for all types of clock noise. Okay. Now, an important point is that this Allen variance, it corresponds to the classical variance, but only when you only have white frequency noise. For all other types, it doesn't. And I just also want to point out that the frequency standard's instability is usually presented as a plot or table of the Allen deviation, not the Allen variance, which corresponds to the uncertainty in the measurement. Okay. So, and just to add some color to this, I just want to show an example where the an example of an Allen deviation versus integration period, and this is for measurements between two ytterbium optical clocks performed at NIST. And in this example, it is white noise. You really only see this for very good atomic frequency standards. Okay, and you can also see there's a few points drifting off of that 1/√² tau line, and that's because those ones were not corrected for the black body radiation shift, which is an important environmental frequency shift in those standards. So this slide explains one of the things that makes the Allen deviation so useful. So if you have output of a frequency standard, you can either look at it in the frequency domain or in the time domain. And it turns out that using this picture where you have the power spectral density of the noise with coefficients in the power law sum, it turns out that you can actually convert between these two representations with the simple transfer function of this power spectral density. And so this example is for the Allen deviation, where you can integrate over this transfer function and actually find these simple coefficients. So if you have a power spectral density measurement, you can convert to an Allen deviation, or vice versa. If you have an Allen deviation, you can convert back to a power spectral density. And this works best if it's not exhibiting all of the types of noise. It works best if it's just one or two. But this is what makes the technique so powerful. And there are other time domain instability measures. So the overlapping Allen deviation is an important one. And it turns out that's the most common measure of time domain instability. And it's equivalent, it has the same expectation value as the Allen deviation, but with improved confidence, because you get to use more points for the calculation. Another important time domain instability measure is the modified Allen deviation. And this one resolves noise types better than the Allen deviation, so it can be very useful for noise analysis and debugging. But an important point here is that you see they're not the same. And so, of course, you have to always say which one you use, and not everybody does. And so there are some ground rules that we want to emphasize for reporting these measurements. So first of all, this is part of the standard, so shall, okay? You have to give the relevant measurement and analysis parameters when you present a measurement. And so earlier versions of the standard had this only listed for the time domain, but we added the frequency domain because it's just as important and maybe even use more. Of course, you have to include the nominal signal frequency and the characteristics of the reference signals, but I won't read all of these. But an important other thing that affects both is the environment. Another ground rule is that any pre-processing shall be indicated. So this wasn't in the standard before, but the working group decided it was very important. And so this includes removal of outliers. There's always glitches in the measurement. You can have a cosmic ray or lightning bolt hit the building or something. And, all of a sudden you have a big glitch that you don't want. You've got to take it out. But all you have to do is say how you did it, and that's fine and normal. And finally, non-random phenomena should also be recognized. And this can include like diurnals from environmental effects, etc. So what else is new? So we added new sections on a few different time domain and stability measures. We added one for parabolic deviation, which is a lot like MDEV, but more computationally efficient. Theo, which gives you better confidence for long-term frequency instabilities. We also added a section on the dynamic Allen deviation. And this figure here is a plot of a dynamic Allen deviation. So it's a three-dimensional plot where you see on the vertical axis, you see the Allen deviation value, and then you see it as a function of time here. And here you just see the time trace of the frequency measurements. But it's good diagnostic when you're trying to analyze effects that are degrading your frequency instability. We also updated a section on time prediction, which is a very important topic. I'm not going to talk about that in detail, though. And finally, we added a section on frequency counters, because you have to know what the frequency counter is doing. The windowing function can dramatically change what you're measuring. We added a section on frequency spurs and another on Bayesian statistics for finding confidence intervals. But finally, and I don't expect you to be able to read this, but I'm going to show it anyway. This is my last slide about characterizing random instabilities. But earlier versions of the standard focused on the Allen deviation and the conversion factors between the time and the frequency domain. But we decided to include conversion factors for multiple different time domain estimators. So we included it for MVAR, or the modified Allen variance, HVAR, Hadamard Allen variance, parabolic Allen variance, and time variance. And we also included a new noise type that's visible in optical frequency comparisons over optical fiber. And it goes as the frequency cubed, 1 over the frequency cubed. So we decided to do this for completeness, but we also wanted to emphasize the difference between all of these different types of measures. So you could take a look and compare the coefficients and see, oh yeah, if I used PDEV, I'm going to get noise that's a little higher, or whatever. We just wanted to be able to emphasize the differences. Okay, so now I'll just switch gears and talk a little bit about the other standard that we worked on, and this one is called Guide for Measurement of Environmental Sensitivities and Frequency Standards. And I'll just say a few words about guides in general. So a guide is a document in which alternative approaches and good practices are suggested. It's not a standard. And so you don't find the word shall as much. But we did use it. I counted, there's about 12 times. It's, you know, and some of us on the working group were a little disappointed because we would rather make it a standard. That can be work for a future committee. But I just want to say it's kind of like a review article, and it tells you methods you can use to measure environmental sensitivities. But one of the most significant changes that we made was we added, we basically rewrote the first few chapters that had the mathematical background to set it all up with a framework for how to express sensitivity coefficients. And this didn't exist in the previous versions of the standard. It's simple. All we have is we have a fractional frequency that depends on a whole series of environmental sensitivities. It's a whole set. And then we expand that into Taylor series, and we keep the terms that we want. And this is simple, but like I said, it wasn't there before. But it makes it easier to describe all of the effects, to have this basic framework. And for convenience, then we also defined the sensitivity coefficients. So the linear first order sensitivity coefficient alpha, it's just the partial derivative of the fractional frequency with respect to one of those environmental sensitivities. And then you can have second order ones too that are just have two partial derivatives. But this was an important addition to the standard. And I'll just give a quick example. If you have a frequency standard whose primary environmental sensitivities are to temperature, humidity, and pressure, then you can write out all of the terms to second order. And if the temperature sensitivity dominates, then you can ignore some of the cross terms for second order and come up with an equation that looks like this, which is pretty complicated. But this temperature, humidity, and pressure, these sensitivities are pretty common in frequency standards, and they're also often interdependent. And so if you really want to be able to predict what the clock is doing, if you're measuring all of these environmental parameters, you do need something like this. And so you can start measuring all of these different coefficients. But if you're a manufacturer and you want to specify something, you don't want to do it like that. And so we decided to give some options to manufacturers for how to specify temperature sensitivity or any environmental sensitivity. This is an example for temperature sensitivity. So here you have a plot of this fractional frequency deviation delta y versus temperature. The plot goes from -40 to +80 degrees Celsius. And this is not a real frequency standard. This is just hypothetical. But here you can see that the fractional frequency changes by about 5 parts in 10 to the 12 over this full temperature range. So one of the ways that you can easily express this sensitivity is with a quantity called total sensitivity, and that's the maximum excursion of the frequency standard output over the specified operating range of the environmental parameter T. And so in this case, it's 5 parts in 10 to the 12 over that full temperature range. That's a simple way to express it. You can also still use sensitivity coefficients even though it's highly nonlinear over part of the range. So that's an option. For example, here, the sensitivity coefficient alpha t for the differential change of the frequency standard over the range from 0 to 30C is a part in 10 to the 14 for C. Or finally, you can also present a worst case sensitivity coefficient. In this case, it's up here at the highest temperature where the slope is the largest, and delta y, delta t is 2 parts in 10 to the 13 per C. Okay. We also gave some specific examples on how to specify a retrace. So these are just a few examples. You can go and look at the standard. I just wanted to give a few examples, but retrace, it's the extent to which a frequency standard returns to the frequency it exhibited prior to turn off after you cycle the power off. And this time interval for the turn off has to be long enough to ensure that the device fully transitions to an off state. So if it's something that's heated or temperature controlled, you have to give it time to go back to room temperature and then back to its operating temperature, for example. And this is a figure that was in the original version of the standard that shows a retrace measurement. It has the fractional frequency on the vertical axis versus time on the horizontal axis. And you can see that after turn on, the device goes through an initialization period and then an equilibration period. And after turn off, when you look at it again, you see you get a different value. And the retrace is the distribution of those values that you expect. But to specify it, you have a few options. So you can do it as a not to exceed specification. For example, retrace not to exceed a part in 10 to the 10 after 4 hours of operation. You can also specify it with a distribution where you say, for example, retrace is plus or minus 5 parts in 10 to the 11 after 4 hours of operation with a 95% probability. And finally, I'll give one more example. And this is a new annex that we put in the standard that gives guidance for measuring a temperature coefficient when you have very small temperature sensitivity in a real frequency standard. So you can see here on the left-hand side, there's a plot of fractional frequency versus cycle number over time, and it has some drift or aging. It has linear and quadratic drift and aging. And the frequency standard is in an environmental chamber so that you can modulate the temperature by plus 10 degrees with some specified duty cycle. And we give the example of how to extract the frequency sensitivity from this. And so after you remove this linear and nonlinear drift and aging with some curve fits, and you can take the correlation function and you can read right off the correlation function amplitude and use a simple equation there to find that linear temperature sensitivity. And in this example, the noise was 100 times, or pardon, the actual frequency sensitivity was 100 times less than what you see here. So if you didn't use this technique of correlation functions, you wouldn't be able to figure it out. So that's a nice new addition to the standard that we added as well. So, I'm coming back to the standards development process. So I've presented some of the things that we did with these standards that were recently revised, and both have been approved by the IEEE Standards Association Standards Board. One's been published, the other will be published soon. But let's just go back to this process. So you see the process is a circle, okay? But you see there's another step after gaining final approval. And what's this? We thought we were done. But it turns out you have to maintain a standard. And what this means is that even when you think you're done, you're not, because it's a circle. And the main thing you have to do to maintain a standard is to keep its relevance by handling errors, which are inevitable, unfortunately. Even if you submit a perfectly edited standard, you'll find that the standards editors will introduce errors. So, and unfortunately, we already had to do an erratum for IEEE 1139. But an erratum, it's like an erratum for a paper. It just contains corrections to editorial mistakes made in the published standard. It does not need to be balloted, so you can do it in like a week, as long as the editor understands what you want to change. But then there are a few more involved types of ways you can handle errors. One is a corrigendum, where it has to go through the full process. But it can be easier if there's just a few errors, hopefully, because this is what we're going to do with IEEE 1139. So if you guys read it, and you find more errors, please let me know, because we will be submitting a corrigendum. Also, you can do an amendment, and that may contain new material that you can incorporate into an existing standard, and you also can incorporate substantive corrections or new material. So I'm getting close to the end, so I just want to highlight a little bit of other frequency standards, frequency control standards work, and namely, maybe some of the folks in the room are actually on one of these committees, but I mainly want to emphasize this new standard that's currently being developed. It's called IEEE 1952, and it's a standard for resilient positioning, navigation, and timing PNT user equipment. And this document plans to specify the technical requirements and behaviors for resilient PNT equipment. And the scope is pretty broad, actually. But it's limited to reception, ingestion, processing, handling, and output of PNT data. It covers a lot of ground. They're also planning to define different levels of resilience to enable users to select the level that's appropriate based on their risk tolerance, budget, and application criticality. I just wanted to highlight that. It's still possible for you to join that working group if you are interested. And that's it. I just want to thank you all for listening, and thanks again for the invitation. I'm happy to answer any questions.
Okay, so do we have any questions?
Hi, Christine Hackman from NRL. First of all, thanks for all the great work on the previous standards and guides. Could you say a little more about what's coming in with 1952, like who's pushing for it, et cetera, et cetera?
So it's possible there's some folks in the room who know more about this than I do. I just joined the working group as a non-voting member, haven't attended any meetings yet. But this was work that was pushed by the Department of Homeland Security to try to standardize receiver equipment, I believe. The working group is being led by Shelby Savage at MITRE, and it's a very well-organized group. I've interacted with them by email, and they're still kind of in the early phases of this work. So I think they have a few more years before their time is up, and so I think the work is starting to pick up now.
Hi, this is Doug Arnold from Meinberg. I'm actually acting as the technical editor for that working group, and I am giving a presentation tomorrow morning in the PTTI session on that working group's activities.
Any more questions?
You mentioned that there's kind of a legalistic aspect to this, and the word shall features prominently. Is there some kind of enforcement branch?
Just shame from colleagues if you don't know about that.
Other questions?
Hi, Chris Flood from the University of Colorado. Thank you very much for your talk. It seems like a huge technical undertaking, and I'm curious a little bit more about the process. So from like a previous version to like a version that you write, what percentage is novel, or how much do you use from previous versions to write your version?
Thanks, that's a good question. And so the standard on random instabilities, I mean, the basics haven't changed since the first version was published in the 80s. There are more types of estimators for the Allen deviation or modified Allen deviation than there were back then now. And I'll admit, so I'm an atomic physicist. I'm not a mathematician or a statistician. And so if it didn't make sense to me, then we had to rewrite it, which was the basic criteria. It turned out there were some things that didn't make sense to anybody on the working group. And so we spent a lot of time just to try to make sure things made sense. So a lot of it was just editing of the text for the random instabilities standard and adding new methods that were developed since the first versions were published and just updating the references. For the standard on environmental sensitivities, that was a much, much bigger undertaking. So the standard itself was twice as long. It took us twice as many meetings of the working group to discuss all the revisions. So different members of the working group each took different chapters. And so I edited the first few chapters, and then individuals worked on other chapters. And we all met as a group to make sure that it made sense and that we were describing it properly. But we rewrote most of the document. And we also included things that weren't in there before, because the original version tended to focus more on quartz oscillators instead of the environmental sensitivities of atomic frequency standards. So we introduced some discussion of atomic physics in the process also for specific sensitivities that primarily affect atomic frequency standards. But it was a big job. But it didn't end up longer because we moved a lot of stuff that was in the chapters that was kind of superfluous or not part of the basic standard. We moved it out or moved it to an appendix. And so we kept it the same length even though we rewrote the whole thing. Thanks.
Over here? Over here? Oh, okay, we can do him then.
Quick follow-up, is it still relevant then to quartz oscillators?
Yeah, I mean, we just tried to make it general, but since it's a guide, we're telling folks how to make these measurements, so, you know, certain things only affect atomic standards, so it should be relevant still. It's just more inclusive now.
Next question?
Hi, you mentioned that the 1952 standard is so people can still join and stuff, but for standards in general, what sort of qualifications does somebody need to get involved in this?
You don't need any qualifications. You just have to be interested. So anyone from anywhere around the world can join the working group. But for you to be an integral part of the working group, you have to attend all the meetings and contribute. But you know, you can also join as a non-voting member, and they prefer that if you're not going to attend all the meetings, because otherwise you can't get a quorum. But you know, for these, I was pretty happy with all of the colleagues. We always had a quorum, and everybody was a voting member, and we also made all decisions on consensus. So we only really voted once or twice, and otherwise everything was unanimous consent.
Okay, thank you.
I think we have a question over here.
Hi, Wei Min Zhou from ARL. I have a stupid question. So hypothetically, if you have a frequency source, the signal level is very low. It's very close to thermal noise floor. Then how do you define the Allen deviation to measure the power spectrum density because you couldn't effectively separate them.
So in that case, I mean, you can always measure a time trace of the frequency, and so you can always plot an Allen deviation. For actually making a measurement of the power spectral density, it might get tricky because somebody else, maybe Tom or someone, should who does this every day or often, should comment on this. But you basically have to have a phase lock that you lock to the signal to measure the deviations, and with a better reference. In this case, it wouldn't be hard to get a better reference, but doing the lock might be hard if you want to measure phase noise.
Hi, I'm Shishir from GMB UK. I have two sub-questions. So first is, how often these instability standards are revised? And second, are there's some deadline when academic institutions or industries are advised to stop using old standard and start using new standard?
I'm sorry, but I didn't hear the beginning of your question.
So how often these instability standards are revised?
How often are they revised?
Oh, so they have to be revised every 10 years, but you can do it sooner. You can do minor revisions with a corrigendum or amendment, but you can also just submit a project authorization request to the IEEE to completely revise it. We could do that now, but we're not going to do that now, unless there's somebody else who wants to be the working group chair.
I think we have time for one more question. I have a quick question. How do we get these standards, and do we have to pay for them? Because I was going to look for the 1139. I didn't realize it came out already, but I've been eagerly telling everyone about it. So.
Oh, okay. So you can find them on the IEEE Standards Association website. You can also see them on IEEE Explorer, but they aren't free, unfortunately. But you know, you can get the PDF anyway. So there you go.
Okay, let's all thank our speaker. So we have one more part between you and lunch, which is the exhibitor presentations. They're going to be led by Francine Vanicola. And I'll bring her on up.
So good morning. This year we have 16 exhibitors, some new to the conference, and welcome, and some have had some name changes over the last year or so. Exhibitors provide significant support to the PTTI ITM conference. This session provides the exhibitors the ability to highlight their current and new GNSS time and frequency products. So they are set up right where we will be having our luncheons, and I think just lunch. So anyway, we would encourage you to visit the exhibitors, and each one is going to come up and do a 2 to 3 minute presentation on their product. So the first one up is Brandywine.
Hi, good afternoon. I really don't want to be between you and lunch. I know it's important. So Brandywine Communications was started in 1995. My name is Alana Diashenko. We are based in Southern California and concentrate primarily on aerospace and defense. Our product portfolio include anything from embedded small timing cards from miniature mini PCIe to VPX, 3U VPX and PCIe, compact PCI cards as well, and rugged master clock timing systems, all with redundancy between power supplies, oscillators, and also alternative PNC input. The products that we showcase at this PTTI is a 3U VPX card, and we also partnered with Oscillocords Adver and presenting optical cesium, as well as the new M-code card for 5422. So the next is CAS navigation.
Hello everybody, it's my pleasure to introduce you our company Cycle from Hamburg in Germany. My name is Michael Hagemann. Cycle was founded by Professor Franz Kärtner with the goal to deliver low noise timing and synchronization solutions to our customers. We transfer cutting edge research into reliable products for scientific facilities and industrial applications. For the transfer of frequency signals with ultra-low timing jitter, we offer two products with different approaches. On the left side, you see our wave timing link, which is a fully automatic RF over fiber solution with an integrated timing jitter of smaller than 40 femtosecond root mean square. It's a compact and simple system using a continuous wave laser, which is compatible with common electronic phase detection and microwave equipment. On the right side, we see the pulse timing distribution system, which uses the inherently low noise pulse strains of a mode locked laser. To achieve sub-femtosecond timing distribution. The use of our balanced optical cross-correlators for laser-to-laser synchronization and balanced optical microwave phase detectors for laser-to-RF synchronization ensure minimal timing jitter between master oscillators and all devices in your facility. Moreover, the pulse timing distribution system is compatible with current and future optical clocks and frequency clocks. Both timing distribution systems are able to preserve the frequency stability of state-of-the-art masers on all timescales, which can be seen in the LNDA2 plot on the right side. This is true independent of the type of device at the remote location that shall be synchronized to the master oscillator. In addition, both timing distribution systems can be implemented with active fiber link length stabilization to compensate for fluctuations of the environmental conditions. Our technology allows link lengths of up to more than 10 kilometers. If you're interested in our technology, please meet me at booth 2. It will be my pleasure to welcome you there. Thank you.
Hi, I'm Tom McClelland, representing Frequency Electronics. Frequency Electronics has been around for 62 years. I'm personally a product of the baby boom generation, the boomer, and Frequency Electronics is the corporate equivalent of a boomer, Boomer Corporation. We've been manufacturing precision frequency standards for 62 years, and we're proud of the longevity of some of our products. In general, the systems that our products go into don't last as long as our products. We're proud of the fact that we have an oscillator on one of the Voyager spacecrafts, which is still operating 40 plus years. I don't remember exactly, 45, 46, 47, keeps going up. We have many frequency standards on other satellites, but typically those satellite systems don't last as long as the oscillators. We do atomic clocks, rubidium atomic clocks, in addition to quartz oscillators, and of course a lot of microwave systems for military and satellite systems. And one of the things that FEI is known for is that we manufacture pretty much vertically integrated. We start out with raw materials, quartz. For quartz oscillators, we manufacture the resonators at our in-house facility. And for the atomic clocks, we manufacture the cells, et cetera, that go into the atomic clocks. We have recently completed the qualification of a digitally controlled rubidium atomic clock that's designed for satellite, very precision GNSS satellite applications, shown on the left-hand side. We also have a subsidiary out here in California that does GNSS time and frequency systems, and we manufacture a lot of receivers, tuners, synthesizers, and frequency converters for various applications. Looking to the future, we're developing a pulsed optically pumped rubidium frequency standard, replacement for the more conventional lamp-based rubidium vapor cell atomic clocks. This product is anticipated to have about an order of magnitude improvement in performance compared to the lamp-based products, and we anticipate that prototypes of this will be available in approximately 1 year's time. Thank you. Oh, one last thing. We are hosting a hospitality suite tonight from 5 until 9. And you can visit us in booth number 16 in the exhibit hall. Thank you.
Hello, ladies and gentlemen. Great to see a lot of familiar faces as well as some new faces. I hope you all come and visit us at the booth and learn about all the wonderful things that we are doing. My name is Ron Segura. I'm the CEO for GuiTech. Since 1988, GuiTech has been designing, manufacturing, and selling very high precision frequency counters and time interval analyzers. We basically target the labs as well as manufacturing. We have a slew of products that are PC-based. We sell them as computer cards for those who would like to install them and in their systems or embed them in their systems. But we also have them in a rack mount that scales up to 24 channels. We have them in a benchtop instrument with a beautiful touchscreen display, as well as in a portable cigar box size instrument. Those instruments are very, very high precision, but we also have them in as low as 40 picosecond for those who do not need the very high performance. Some of the applications are like Allen deviation, network monitoring, 1 PPS monitoring. We have developed a beautiful application, much like what you probably are familiar, that used to be the Symmetricom microchip application. We have developed for 1 PPS monitoring as well, and it's available with the instrument. And for those of you who would like to get an out-of-the-box, say, entry-level instrument, PC, we integrate that and we promote it as an out-of-the-box easy solution to use. Any questions, please come and see us, and thank you so much.
Hello everyone, my name is John Clark. I'm the president and CEO of Master Clock Incorporated. Rather than go over some of our products, I'll just introduce our company real quick. We were founded initially in the early 90s, coming out of the broadcast industry, focused on radio synchronization. Eventually grew into a global company providing a range of generation, transmission, and display products for the time and frequency industry. What's interesting about us is we're located in suburban St. Louis, Missouri. We've got a development office out in Sunnyvale, California. We are not a silo of another organization. We're not a side gig. We're not a subsidiary. We're a privately held company that focuses on this as our mission. And we look forward to having you come up to our booth, find a little bit more about our in-house manufacturing, how we do custom integration, consulting, support, optimization services. It's not just always what's next, but how do we take what we have and make it better, make it more sustainable and more useful. And that's what we like to focus on. So we want to hear your challenges, your problems, the things that keep you up at night related to time and frequency, maybe not batteries and urban air mobility. But we're here for you. We want to make time for you. So thank you.
Hi everyone, I'm Shiro Anto with Microchip. I'm really happy to be here, all you great people. I'm with Microchip Frequency and Time Systems. I want an array of solutions from synchronization products, government solutions which are highly specialized, atomic clocks, and crystal oscillators. We have examples of all of these technologies in our booth today. So I hope you'll be able to come by and see some of the latest innovations in these areas. We're at booth 11, and a couple of things we have there is a two-way space-time transfer solution that we'd like to explain to you. We also have a solution for very small atomic clocks. We call them the embedded atomic clock family. Those are both rubidium and cesium based, as well as low noise options for those highly portable applications. We've developed some new software called Clock Studio, which makes it very easy for new engineers working on new projects to interact with our atomic clocks. It's compatible with all of our atomic clocks you see on the picture there, and will be actually being upgraded to apply to more of our solutions over time. So it's a great new tool. And we'll also be talking about a time standard to allow you to create your own time reference. And I apologize, I'm going to miss it here. Always bring your glasses. Autonomous timescale, I apologize. So we developed some technology to allow you to ensemble different types of clock sources. We've developed some very clever software for basically the ability to have your own autonomous timescale and start small and make it as useful and as powerful as you want. So please come see us after lunch. And I hope some of you were able to attend Dr. Robert Lowak's talk yesterday's tutorial on atomic clocks. I think it's a fascinating topic. And over this week, we have 3 further talks today. Right in the middle there, Zhang Li Zhang. Don't embarrass him, he's right in the back corner there. He's going to give us a glimpse of the future. He's going to give us an update on the ytterbium ion atomic clock innovations that he's working on with our team in Beverly, Mass, focusing on the lower size, weight, and power version for tactical and portable applications. And tomorrow, Dave Chandler is going to talk about the 5071, the classic cesium beam tube reference, and how the work that we're doing at Microchip is going to give that a healthy, strong, modern design well into the next decade. So he'll give us an update on that tomorrow. And then on Thursday, don't go anywhere, but Will Kerswick, my colleague, is going to talk about a rubidium solution called the miniature atomic clock, and he's going to really make it practical. He's going to explain to you how to interpret the specs on the data sheet with some real-world mission profiles, and how that can impact performance, and how you should be able to predict it ahead of time rather than find out later. So lots of interaction. We also have some of our executives here and some of our business managers. So please make sure to look us up and come talk to us. Thank you so much.
Hi, my name is Gary Guy. I'm the president of Orca Technologies, and with me today is Matt Fishman, who's our Vice President of Sales and Marketing. We're one of the new companies that Francine mentioned earlier about as far as exhibiting here at the PTTI conference. But we're not really new. We've been in business for well over 15 years, starting out primarily supporting airborne and portable timing instrumentation. But really, our experience is well over 30 years. Many of our engineers and product managers, including myself, came from other companies actually exhibiting here today. Just curious, does anybody remember the name Datum or True Time? Oh, okay, a few hands. Well, that's where we came from. So, and now they're the Microchip Group, really good company. So we're with the years of experience and with the technology and our engineering team, we've really come up with some innovative and fresh product ideas. Many of the companies that we support today are from the aerospace industry, the national test ranges, laboratories and such. In fact, we were awarded several prime contracts last year in support of an upgrade of a timing system for one of the ranges, and perhaps actually one of our customers might come out and talk a little bit about that here. Matt's going to talk a little more about our rack mount and portable products, as well as our traveling clocks and the new things that we're doing here, and look forward to working with you on any customer or custom type product developments. And one thing that we'll always do at Orca Technologies is provide technical support.
So as Gary mentioned, we started out in a very portable type of business where customers would want to take out a very low power, low swap type of product into the ranges and jam time into, let's say, a camera type application or anything like that. But a lot of our customers actually drove us into getting into the rack mount business where we can do different types of time and frequency signals from pulses to frequencies, including network timing as well, which you guys probably are familiar with NTP or PTTI. So we've created a new product called Trestles, which is our most advanced and most capable and flexible product that we have to offer. Okay, I thought I was loud enough, but all right, I apologize. So I won't go through all of that again, but I'll move on to the very next slide where we've actually taken capability from our Trestles product and we've actually mounted it inside of a battery-operated Pelican case, which one of our customers actually funded us to do. And what this is primarily used for is for keeping very precise time over a long period of time, such that a customer could go into some sort of cleared facility where they need to go underground or anything like that and jam time into a missile that's in a silo or even submarines or anything like that. So it is actually on display at our booth right now. It's battery operated. It can last more than 14 days in what we call low power mode. So please stop by. Look forward to talking with you guys and helping out with any type of problems that you guys have at this time. Thank you very much.
Well, hi everyone. Some of you are familiar faces, some are not. I've been here a couple of times before. I'm from Pendulum Instruments, a company with 60 years experience in the field of frequency and time measurements. Our oldest and our core business is the frequency counter analyzer family, where we have several models covering up to 60 gigahertz of frequency range. We have been pretty successful in selling all over the world, tens of thousands of these boxes, and a couple of thousands to the US military, both the Navy, Air Force, and Army. Other families are time and frequency references with OCXOs and rubidiums focused on traceability and portability. We have frequency distribution products to be able to distribute both sine and pulses over fiber as well as coax. And then we have two newly acquired Swedish companies. One is Detectus, making EMC scanners for pre-compliance EMC testing, and FLC Electronics, making high voltage linear amplifiers for anyone who needs higher voltages from 100 to 1600 volt peak to peak. Our latest development is the counter analyzer CNT104S. It's a 4-channel combination of a universal frequency counter and a time interval analyzer. It's the world's first 4-channel frequency counter that can replace, for example, 4 traditional frequency counters in a counter test system in the same box, because every channel is independent of each other. It performs 0 dead time measurements, has 7 picoseconds resolution, and can make measurements up to 20 million samples per second. It also has an additional RF channel up to 24 gigahertz for frequency measurement only. We can present the data in 4 different modes: 2 numerical, parallel values, or parallel statistics with all the relevant statistics parameters, including Allen deviation on the same screen, and 2 graphical modes for viewing values versus time, and the frequency distribution of the acquired values. Please come and stop by at our booth, number 3, and I will be happy to tell you more about it. Thanks.
Good afternoon, everybody. Some of you might know us as Aurelia, but we were recently purchased by Safran, so now we are Safran Electronics and Defense. But it is the same group, same people, same products that we've been doing for the last 30 years. At this show, we have the Switzerland-based group, which is mostly atomic clocks and oscillators. And these are the 4 groups here from the left to right: iSource, the iSync, the iSpace. iSource would be the non-disciplined products. The iSync would be the disciplined products. And of course, the iSpace for space. We're known for the Galileo project, where we are the sole provider of atomic clocks and masers. And of course, we have some test lab equipment that can be used in different ways. Our featured product is the miniature rubidium clock, which is the MRO 50. This one here is the standard one. We also have now released a new rugged one for high vibe and shock and extended operating temperatures. And we will be releasing a 1 PPS MRO 50 probably in the next few months. Thank you very much. Hope to see you.
Good morning, my name is Franklin Askeruns. I'm here with Maria Delgado, representing Spectra Dynamics. We're a company that's been in business for about 29 years almost. We are making, well, we've been known to make frequency and pulse distribution amplifiers for timescales. But we have added over the years microsteppers, specialty microwave synthesizers, and we are now manufacturing a cold rubidium microwave atomic clock. And we're venturing into the optical space with some interesting optical to microwave converters. So this is the atomic clock that I was talking about. This was developed under a DARPA program, and it is now commercially available. So you can see that on the performance chart on the upper right, that the ADA, the Allen deviation, total Allen deviation of the clock can be represented by 8 parts in 10 to the minus 13 over root tau, and reaches a floor of around a part in 10 to the minus 15. So we're now on clock number 18, and we have been shipping these for the last 2 years. For folks that are wondering how to convert from optical to microwave, we have some converters that we've developed over the last 3 or 4 years, so that you can provide your user a standard output at 100 megahertz, 10 megahertz, and a pulse per second output that is, of course, tied to your optical standard. So typical performance is listed up there on the ADEV. Out at 1,000 seconds, we're in the mid-17s for stability. And of course, the phase noise is superb, with a floor around -178 dBc per hertz. So if you're interested in talking to us or in one of our products, or you would like to see one of our new distribution amplifiers that now has monitoring and control over Ethernet, and switching, and we can build these up to gigahertz. Please come visit our booth. It's booth number 6 in the exhibit hall. Thank you.
Hello, everybody. Good to see that we're finally coming back here in person. I think we're nearly at our numbers that we were at pre-pandemic. I'm Jeff Martin with Spirent Federal Systems. We've been around quite a while, been attending these events for some time. I know we're all getting hungry. I promise this will be brief. I think we're towards the end of the alphabet here. Just some quick notes there about Spirent. We've been around quite a while. We are PNT test equipment providers. I think we're most notably known for our GNSS simulators. Many of you have our equipment in your labs. Some quick notes here on places we've been and things we've done. We've been the first with many things. A little bit of a bragging chart there on the left with just some of the folks we work with. Not nearly representative of everybody. We were first with Galileo, first with M-Code, and down at the bottom there, 2022, doesn't mean a lot to this audience, but it was a big deal with our partners in the UK, the Queen's Awards, so a fun note. As I said, mostly known for GNSS test equipment. We have a number of simulators over on our stand at booth 14. I promise to be brief. Just stop in and see us there. We'll show you what we've got. Thanks.
Good afternoon, everyone. I'm Jamil Bashair from Vector Atomic, where we're operationalizing quantum technology for navigation and timing. We're not as old as some of the companies that have been here. This is our first time at PTTI. We're founded in 2018. We're at 40 employees. We're located in Pleasanton, California, in the Bay Area. Our focus is really on developing optical atomic clocks, time transfer, and atomic inertial navigation systems. So current focus for us is on fielding prototypes, and you're seeing the fruits of our labor here in 3 systems we've taken out into the world with the goal of having commercial products in the next 1 to 2 years. In order to get all this stuff into these boxes, it really requires us to develop a lot of technology in-house. So many of our subcomponents and all of our subsystems are developed in-house, and you're seeing that in terms of vacuum systems, lasers and optics, and electronics. At PTTI, we're going to be talking about 2 demonstrations we've done on deployable hardware for picosecond level timekeeping. The first talk will be given by John Rosland, and he's going to be talking about a demo we did at RIMPAC 2022 where we operated 3 optical atomic clocks on a ship for 20 plus days. Next talk will be given by Armand Singes, where he'll be talking about femtosecond level time transfer over free space, over 30 kilometers, doing, again, synchronization at femtosecond level. So all the hardware that we use for these demos is on display at our booth, number 10. Feel free to come by and chat with us and hopefully come to the talks. Thank you.
Hello and good morning, or maybe it's afternoon by now. Can you hear me?
Yeah, I hear you.
A little closer? I'll see what I can do. If you can hear out, you should be able to hear me. I'm Michael Radunsky. I'm with Vescent Photonics. We are a picks and shovel company. We like to make tools to make other people successful. And the reason that we're successful is the people that we have. Some of the folks in our company have been very close to seminal work in the photonics industry, developing instruments that are useful for all sorts of people. Mike Anderson was our founder and co-founder and been our CEO, but now he's our chairperson. He was the first person to observe, with of course his team at Eric Tornell, BEC, which makes a lot of quantum sensing possible, which is going to enable the next generation of optical clocks. He went on to found our company and made a big difference to all of us. Kurt Vogel, the VP of Technology, made some of the first measurements with optical frequency combs, and this facilitated the kind of products that we offer now. Vescent is a small company in Golden, Colorado. We have about 40 employees and about 20,000 square feet of workspace, including 2,000 square feet of clean room. I put up this picture of Kurt with the frequency comb there. The frequency comb is one of our seminal products for the time and frequency community. When you stabilize a frequency comb, you have very stable wavelength reference across the spectrum, and you can also convert that stability to the RF spectrum too. So our goal is to get as many measurement devices out in the field as possible, and those based on optical spectroscopy have a long history of trying to get in the field, but not necessarily getting in the field. So if you look on the left-hand side, you see Ted Hensch's first optical frequency comb, and it's a typical laboratory snare of cables and optics and components. And we're trying to simplify that. From that and other physics experiments, we've developed products such as CW lasers, very stable and high bandwidth control for starting the physics that can be used in an optical clock. Other optical components such as frequency standards, detectors, etc., come in that line. We also pride ourselves with our electronics, our control electronics. These electronics are extremely low noise, high speed for control of your laser systems as you may need them. We also have developed a line of frequency combs, which again are the backbone for optical clocks. Every frequency comb, every optical clock is going to need a frequency comb, and so we have in the middle here laboratory devices used for developing products. And then on the right-hand side are deployable OEM modules, products that we think are ready for the field for doing optical work in the field. A lot of folks have said that the optimum number of lasers in a system is 0. We're here to fight that. You can use lasers in the field. You can make measurements successfully in the field. Unlike most laser manufacturers, we're trying to, as I say, build these to deploy. We are running our products through shake and vibe and temperature cycling to prove that they're field ready. So if you want to hear the whole story on this, come and hear Kevin Kanavi speak at 1:45, I guess in this room right here, and visit us at booth 19. Thank you very much. And we can all go to lunch on that.
Yes, this is the end. Lunch is being served upstairs, and then the sessions resume 1:45-ish. I know PTTI is 1:45. Thanks.
Trust